Me again, number 6.
So it's talking about the change of entropy.
Yes.
Versus
Maybe. I'm not familiar with the question, so make no assumptions with me.
basically, that's so he's saying you have these two molecules that are the same equation, just different formation.
Oh, hold on. So not equation, same formula, different structure.
That's what
All right, we're getting closer. Keep going.
and it's saying like A is saying which will have the higher entropy change, and B is saying which will have the lowest entropy change.
Oh,
Elimination,
yes,
so, the elimination will have more entropy.
yes.
But I had somewhere in my notes from class that entropy is the opposite from entropy.
Okay.
Is that all in physics?
Did you say enthalpy is always the opposite of entropy? Is that what you said? That's not true. No. Can we just fiddle with number 6 for a minute? So, guys, looking at number 6, there's a term here that you need to know, and that term is isomer. You guys are getting comfortable with the idea that homework is not always just a summarizing process. It's also a learning experience. So, guys, this is a term that you need to know, but conveniently they define it for you. So, guys, isomers are molecules with the same formula but different structures. And they show you 2 examples. Guys, hydrocarbons love to form isomers. It's one of the things that makes organic chemistry horrible. But it says you've got 2 isomers of pentane. One is called N-pentane, it's stretched out. The other is called neopentane, and it looks like an X. And then it goes on and it says, do you expect a significant difference in the enthalpy of combustion? Now, guys, let's talk. When we talk about enthalpies of combustion, where does the energy go in? Where does the energy go in? In all reactions, where does the energy go in? Breaking the bonds of the reactant, right? Where does the energy come out? Forming bonds in the products. So, guys, the idea here is because we have functionally the same type and number of bonds in both of these isomers, we would expect the same amount of energy to go in. We would also expect the same amount of energy to come out. So the enthalpy change should be about the same. But then it says, which isomer do you expect to have a higher standard molar entropy? But guys, notice that it is not saying an entropy change of combustion. It's just saying which one of these is messier. And what's the principle? Which one's got more messy, long or clumped together? Long. So we would expect the N-pentane to have a higher entropy. So question A is about combustion. Question B is about which one's more mixed up. Is that okay? Okay, but be careful about trying to think that there's a relationship between those, because there isn't. We are going to talk in a minute about the relationship between enthalpy and entropy, but that's called Gibbs free energy, and we'll get there in a minute. Okay, what else, y'all? Yeah? Probably not. Are they hard? I'm not very good at hard. Okay, C and E. Oh, my book is so far. I'm going to make it. Number 11. So guys, the question on the table is number 11, C and E. It says, which of the following processes are spontaneous and which are non-spontaneous? So letter C says the reaction of nitrogen to form nitrogen molecules. Now guys, think about this. And maybe you can't think about this, but if you find nitrogen in nature, do you find nitrogen atoms or nitrogen molecules? Nitrogen molecules. So we know that forms spontaneously because it's what we find. And so the idea is that this is spontaneous because you don't find nitrogen, you find nitrogen molecules. Is that okay? Okay. Then looking at E, the formation of methane and oxygen from carbon dioxide in water. So this is the opposite of our Bunsen burner reaction. So we talked about the idea that Bunsen burner gas, CH4, reacts with oxygen to make carbon dioxide in water. And we said that was spontaneous even though we had to add energy. Do you remember that idea? The spark doesn't make it not spontaneous. Weird sentence. So we've got methane, oxygen, carbon dioxide, and water. What this is saying is carbon dioxide and water turns back into methane and oxygen. And that we don't see happen, so it's not spontaneous. Is that okay? So fundamentally, if something's spontaneous, it means you see it happen. What else, y'all? Can we be done? Oh, no, go. 21b, yeah. So it says, consider a system consisting, I love ice cubes because I can picture them. Consider a system consisting of an ice cube. Under what conditions can the ice cube melt reversibly? Reversible means spontaneous. That would be at 0 degrees Celsius. Then letter B says, if the ice cube melts irreversibly, is delta E 0? Yeah, irreversible. So doesn't it say irreversible? No, I read it wrong. I'm wrong. So it says, if the ice cube melts reversibly, is delta E 0? And the answer is yes. So the idea is that energy in and energy out are equal at equilibrium. So it... Did I say no? So realize the only person we have to blame for this is me, because these are my answers. Was this 21? Right. Right. And so the energy that's going, is this not what's posted on the website? Oh, guys. Yeah, so if that's the case, I apologize. I need to make a note to myself to fix this. I actually vaguely remember last year my class pointing out to me the answer was wrong, and I changed the answers, but I failed to post the updated answers. So 21, well, I just need to repost the answers to entropy. So sorry, that was my bad. Yeah, wait until you get into college and the only answer set that you have are the answers in the back of the book, and a lot of them are wrong. Super frustrating. So, but that's my bad, sorry. Yeah, so no, that was my mistake. It's fixed now, so sorry. I'm glad you brought it up. Are we done, Christian? You bet. 29C. And it says, do we need to do A and B before we get there? Well, I do, because I don't know what's going on. So it says, what sign for delta S do you expect when the volume of a mole of an ideal gas is increased? So if the volume goes up, it's more space to spread out, more messed up, delta S would be positive. Then it goes on and it says, if the final volume is 18 liters, calculate the entropy change. I was going to say, I don't know how to do that. Okay, so then number 20 says this. Do you need to specify the temperature to calculate the entropy change? And the answer is no, because it's isothermal, which means the temperature is not changing. Yeah, so what's going on in that question is when you get, should you choose to be a chemist, when you get to your junior year in your chemistry study, maybe senior year, depends, you'll take a class called physical chemistry. It's everything that's horrible about calculus and everything that's horrible about chemistry. It's the calculus of chemistry. And it's really where you finally learn what orbitals mean. You solve Schrodinger's equations, all this other stuff. Another thing that you do is you actually calculate entropies for substances. You actually talk about the equations that allow you to do that. And that's what this question is sort of begging, is sort of some of the things that you have to think through when you're figuring out entropies of substances. Go ahead. Yeah, it just means the temperature does. So iso means not changing, isokinetic, and thermal is heat. So it means heat's not moving. Yeah, so how do we know heat's not moving? Temperature doesn't change. Yeah, and so that then, it's kind of a redundant question, because the question says, do you need to define the temperature change? And the answer is no, because it's not changing if it's isothermal. What else, y'all? Good? Okay, so gang, open up. Oh, shoot. I got the hiccups. Guys, open up your books, if you would, to page 809, and let's get in note-taking position, and let's get this recorded. And then we are going to go. Oh, wait, pause or stop? Pause. Good. You should be teachers. Actually don't. Yeah. I remember actually when I decided to become a teacher, and I went and told my very favorite teacher from high school, who was actually a humanities teacher who taught me to write. His name was Mr. Otto. And I walked into the high school Christmas break. We got out before they did. Hey, Mr. Otto, so good to see you. How are you? Good. Hey, what are you thinking about? Hey, I'm thinking about coming a teacher. And he looks at me and goes, you're an idiot. It's like, oh, shoot. It turns out he was right. No. All right. So, guys, here we go. We are now going to wrap up chapter 19. The test is on Friday. But, guys, finally now we are ready to answer the question definitively about and remember, right, the big idea for chapter 19 and therefore chapter 5, because 5 is leading into 19. Guys, the big question was, is a reaction spontaneous? And we've been flirting with that question over the last 3 weeks. We've talked about spontaneous reactions tend to give away heat, right? Say yes. Yeah. And we've talked about the idea that spontaneous reactions tend to increase the disorder of the universe. Also yes. But guys, now what we're going to do is we're going to bring these two potentially competing ideas together into one tight little bundle that is called Gibbs free energy. Now guys, here's the deal. On the test and on the AP test, the hard part about Gibbs free energy is not the math. Grab your AP sheets and we'll talk about that in a minute. The math is not the hard part. The hard part is the conceptual stuff. Does anyone need one? You guys okay? Okay. So guys, the hard part is the conceptual stuff. So let me explain to you the two questions that you're going to see on the AP test about spontaneity. You ready? It goes like this. Conceptually, the question is going to be, is this reaction spontaneous? Let that sink in. Conceptually, the question is going to be, is this reaction spontaneous? Now, guys, understand, in order to answer the question, you've got to come back to Gibbs free energy. I'm going to show you how to do that using the table on page 809 in just a minute. But then, guys, the additional questions that they will ask you are mathematical. One of them will be, at what temperature range is this reaction spontaneous? Frankly, the math there is not bad. And then, guys, the final question they'll ask you, which is also mathematical, is what is the Gibbs free energy change for this process? And you'll see that math isn't bad either. So, guys, the conceptual stuff is tricky. The mathematical stuff is straightforward. And you're going to enjoy all of it. So, you guys ready to get going? Okay, so Gibbs free energy in a nutshell. So guys, going back then to what we just said a second ago, here's where we are. So guys, this is what we've agreed upon so far with spontaneous reactions, noticing that we use some very vague language. So guys, spontaneous reactions include the word tend to. Spontaneous reactions tend to have large negative enthalpy changes. They give off heat. They're exothermic. I want to add the word tend to. Guys, that's one of the things you'll learn to do increasingly in this class is learn to be vague. Because then you have plausible deniability when you get things wrong. There we go. Now it's better. Boom, tend to have large negative enthalpy values, and those are delta H's. In addition to that, all spontaneous reactions tend to cause increases in the entropy of the system. Notice not the universe, but the system. Oh my gosh, because we just had a horrible thing happen. Just a minute. You can't even see it. I'm hiding it from you. Yeah, it is showing up on the screencast though, so you'll be able to see the mess later. Okay, so guys, this then is where we're at. This is then where we're headed. So guys, now we're ready to answer the question. But how do we do it? So what we need and what we're going to produce today is a final predictor of spontaneity. But guys, in order to come up with this final predictor of spontaneity, what we need is we need a way to bring entropy changes and enthalpy changes together in meaningful ways. And guys, the way that we do that is actually through what is called Gibbs free energy. Now, guys, you don't need to know the history of this, but it's actually kind of interesting, or at least I think it is. Gibbs was actually a guy that was trying to figure out how to maximize the efficiency of steam locomotives. What he found is that they were piling a bunch of coal into these steam locomotives, and they weren't getting out all the work, all the energy that they should have, given the amount of coal that they were burning. And so Gibbs was like, wait, where's the extra energy going? Found out later the answer was to create disorder, and that's where we came up with the idea of entropy. But guys, the Gibbs was thinking there's this energy that should be free or available. The word free actually means available. There's this energy that should be available to do work, specifically haul trains cross country. And so as Gibbs was trying to maximize the efficiency of trains, he started thinking about not only the burning of coal, but the disruption, the entropy of the universe, and started thinking about interesting things, which is actually kind of cool because if you think about it, it was an engineer, somebody with practical intentions that actually came up with these really interesting ideas. So guys, let's talk about what Gibbs free energy is. So Gibbs free energy is simply a thermodynamic function. That's not the important part. The important part is what it does, and it combines enthalpy and entropy together into one tight nugget. You ready to breathe a sigh of relief? Finally, an abbreviation that makes sense. Entropy is S, enthalpy is H, but that's not heat. It's enthalpy, right? Gibbs, G. Hey, there we go. One that makes sense. Shoot. Isn't gravity little g?
No, that's gravitational acceleration.
Ah, see?
Gravitational force.
Okay. This is why I don't teach physics. You guys know that about me, right? I have a minor in physics, but when I moved to Utah, I purposefully didn't tell the state of Utah I have a minor in physics, so they can't make me teach it. Yeah,
I would never want to teach that.
No, physics is hard. It's a tough subject to teach because everybody thinks they know what they're talking about, and most of them are wrong, but it's hard to convince them of such. At least in chemistry, we've never seen atoms, so I could be lying to you and you'd never know. So guys, instead of this, what we then is we bring this together as a function. And now we're getting somewhere. So Gibbs free energy is equal to the H, the enthalpy of a system, minus the temperature, Kelvin temperature, times the entropy of the system. But guys, again, we're not going to talk about state functions, but fundamentally, this is an equation that has no practical meaning for us. So instead, what we actually do is we write it in terms of changes. Now we're getting somewhere. Because we have talked in chapter 5 about change in enthalpies, delta H. We talked about how to find them, both through experimentation, calorimetry, and calculation, Hess's law. You starting to realize you should study for Friday's test? So, guys, we understand a lot about delta H. We know that we can get those values through calorimetry. We know that we can get those values through Hess's law, either through computation or manipulation. Guys, we've now done last time delta S stuff. We know that it's products minus reactants. You plug in the numbers, off you go. Well, guys, we're going to bring those together and we're going to talk about delta G. Before we get into the details, though, let's lay out some general ideas. Guys, this is it. This is the answer to the big question. Is a reaction spontaneous? This is the only, well, not the only, there's one other way, but this is the way right now for us to figure out whether a reaction is spontaneous. And here's how you do it. You calculate delta G. If delta G is negative, the reaction's spontaneous. And guys, that's it every time. If delta G is negative, the reaction is spontaneous every single time. We have to denote spontaneous in the forward direction, but it's spontaneous every time.
If it's equal to the zero,
That's the next bullet. If it's zero, it's at equilibrium. Yep. If it's zero, it's at equilibrium. Are those ideas okay? Giving away Gibbs, and guys, think of Gibbs free energy, frankly, as just the same principles. If energy is going out, the process will happen on its own. Gibbs free energy, but the principle's the same. So if delta G is negative, the reaction is spontaneous. If delta G is zero, the system is at equilibrium. Now guys, this is weird. What if delta G is positive? Is it spontaneous? Let's think through this. If delta G is positive, is the reaction spontaneous? No, because if delta G is negative, it is spontaneous. So if delta G is positive, it's not spontaneous. Here's the tricky question. Does that mean nothing's happening? No, it means the opposite is happening. Here's how we say it. If delta G is positive, the reaction is not spontaneous in the forward direction, but it is spontaneous in the other direction. We just wrote it backwards. By the way, guys, as you're writing this down, let me whisper in your ear. This is the gold standard for establishing spontaneity, but you're going to find out in the last week of this class there's another way to do it, and it only works for oxidation reduction reactions, and it's voltage. If you have an oxidation reduction reaction that has a positive voltage, that will be spontaneous as well. And we'll tie Gibbs free energy and voltage together. It's on your AP cheat sheet. But really, the way that we tell is Gibbs free energy change. All right, so guys, breathe in through your nose, out through your mouth. What do we need to talk about? You okay? Are we good? All right. So guys, what we're going to do then is we're going to move forward and we're going to dig into this only a little bit. We're not even going to do the math. You're going to look at this and go, oh, that's comfortable. So guys, what we can do then is we then think about Gibbs free energy in the same way that we understand that when a ball rolls downhill, it releases energy. Guys, that same concept will allow you conceptually to be thinking about Gibbs free energy changes. You can picture energy flow. Now just call it Gibbs free energy flow and you're good to go. But we will eventually be talking about this mathematically. So we understand any spontaneous process, Gibbs free energy goes down. And guys, we can calculate that. Scratch this down with me. I'm going to add the ends. The ends are not in your AP sheet. But guys, this equation is hyper familiar, right? That in the same way that we can figure out delta S values, entropy changes for reactions, and delta H changes for reactions, it's always products minus reactants, the same thing's going on here. You'll be seeing calculations like this. But guys, the tricky bit then is this, interpreting the results. And this is in your AP equation sheet. You don't necessarily need to write it down. But guys, you got to be able to interpret the results. So say that on the test you run these numbers through and you do the math and delta G is negative. Is that reaction spontaneous? Yes, every time? Yes, every time. So guys, when you do this math, if delta G is negative, that reaction is spontaneous. Now guys, watch my hands. Here's then what that means. That reaction goes to products, so it favors products, right? Now guys, what happens if delta G is zero? Going both ways, equilibrium. What if delta G is positive? Is it spontaneous? Not in this direction, but it is in that direction, and that reaction favors reactants. Just a second. Let's let that settle. So guys, these are all the ideas that you need to understand about the significance of delta G. Delta G is zero, equilibrium. Delta G is negative, spontaneous. That guy's making products. If delta G is positive, it's just spontaneous in the other direction, and that dude is making reactant. So let this settle, scratch it into your notes. And then, guys, we've got one huge more thing to talk about. That was a weird sentence. And then we're done. Maddie, go ahead. Oh, are we okay? No. So this F is not final, it's formation. Yeah, F is formation. Yeah, no, you're good. Isaac, please.
I'm just curious. Does Gibbs free energy affect the speed of the reaction?
Wow, keep going. Yeah, go.
Because if it's zero, it's equilibrium.
Yeah.
Negative, it's going that way, and positive, it's going that way.
Yeah.
Does it affect the speed?
That's a brilliant question. Guys, you've got to know the answer to this because the AP authors love to trip students up on this. So Isaac's question is, does the Gibbs free energy value affect the rate, the speed of the reaction? Guys, please hear this. The answer is no. Rate and spontaneity have nothing to do with each other. So guys, you can have a reaction that has a relatively small delta G value and it can go stinking bonkers. Or you could have a reaction that has a large delta G value and it could be slow. So guys, understand that rate and speed have nothing to do with each other. As a result, this sentence is stupid. You cannot say this. This reaction is more spontaneous than the other. There's no such thing as more spontaneous. Guys, either a reaction is spontaneous or it's not. You can talk about how much energy it gives away, and some reactions give away more energy than others, but guys, spontaneous is not a gradient. You're not more spontaneous or less spontaneous. You just are or you're not. And that doesn't have anything to do with rate. Guys, did all of that make sense? Different reactions can give away more energy than others, but it does not make them more or less spontaneous. Spontaneous is a yes-no proposition. Isaac, that was a great question. I'm so glad you brought that up. So guys, what else? Are we okay there? Okay. So guys, moving along then, and are you ready to move along then? Okay. So guys, this is the big deal. Grab your books, pull your books into focus. And guys, I would strongly encourage you to stop taking notes and learn. Guys, don't try to write this down. This is all stuff you know. And what we're going to do now is we're going to take the things you know and we're going to explore relationships. So guys, push your note material to the side. Grab your book and pull it into center. And guys, join me in this conversation. So guys, here's where we are. We understand that this equation is the equation that allows us to identify whether a reaction is spontaneous or not. So guys, let's identify our players in this equation. So on the left, we have free energy. Guys, what free energy change values are spontaneous? Negative, always negative, right? So guys, if that number, delta G, is negative, this dude is spontaneous. Now guys, we've got to include the words tends to. What delta H values tend to be spontaneous? Negative. Guys, I'm scared. Negative. So this is our enthalpy term. And guys, negative enthalpy changes tend to be spontaneous. Now we've got our entropy term. And guys, what entropy changes tend to be spontaneous? Positive. Let's say that again. If delta G is negative, it's spontaneous every time. If delta H is negative, it tends to be spontaneous. If delta S is positive, it tends to be spontaneous. You guys see where this is headed? We're headed to tension. We're headed to a clash. And guys, the idea is this. If you have a reaction, and if this reaction has a negative delta H value, does that tend towards spontaneity? Yes. If you have a reaction that has a positive delta S value, does that tend towards spontaneity? Yes. But now, guys, do the math. What is T? Temperature. What are the units for temperature in this equation? I said it, but did you? Kelvin. Guys, what can a Kelvin temperature never be? Negative. That's why we use Kelvin temperature. Kelvin temperature can never be negative because absolute zero is the basement for temperature. So guys, Kelvin temperatures can never be negative. So that means that this is always positive. So what we're going to do then is we're going to take this term and then we're going to think about it. So guys, it goes like this. If your enthalpy value is negative, change in enthalpy value is negative, that tends towards spontaneity, right? What if your entropy value is positive? That also tends towards spontaneity. But guys, do the math. A positive times a positive will always result in a positive number, but then you're subtracting it, which makes the value of delta G more negative. Do you see how this works? So guys, if this is negative and if this is positive, the only values that this expression can produce are negative delta G values. Does that make sense? You're good on that? But now guys, and so that will always be negative and therefore it will always be spontaneous. Now guys, what about this? What if delta H is positive? Does that favor spontaneity? It does not. Now, what if delta S is negative? Disorder going down, does that favor spontaneity? No, but let's do the math. So now, guys, looking at this term, T is always positive. So if this is positive and this is negative, what values will that always create? Negative, but you're subtracting them, so subtracting a negative is the same as addition, and that makes the delta G value positive. So guys, if this is our setup for delta H and delta S, what are the only values that this expression can generate? Positive, and that means the reaction is never spontaneous. But how do we say it? Never spontaneous in the forward direction, always spontaneous in the reverse direction. So now, guys, what we've got to do is this. We've got to talk about all the tiebreakers. And in order to do that, what we need to do is go to this table. Actually, before we go to the table, let's talk about what we mean by tiebreakers. So, guys, if the enthalpy value... Don't look at the table. Join me at the board so I can help set this up. Guys, if the change in enthalpy is negative, does that favor spontaneity? If the change in entropy is negative, does that favor spontaneity? No. So what then becomes the tiebreaker? Because we know that this has got to be negative in order for the reaction to be spontaneous. And we have one change that favors spontaneity, and we have another change that does not favor spontaneity. So can this reaction be spontaneous? And the answer is yes. But remember that this is the factor that does not favor spontaneity. So if we want this reaction to be spontaneous, does this value need to be big or small? Small. So how do we make it small? Cool it down. Let's say that again. Guys, follow that whole logic. So we have a reaction and we want it to be spontaneous, which means a negative delta G. Hold on. Negative delta H. Negative delta H favors spontaneity. That's working in our favor. But guys, a negative delta S does not favor spontaneity. So if we want this reaction to be spontaneous, we need to decrease the influence, if you will, of that entropy change. So how do we make this impact smaller? Well, we make the temperature go down. And if the temperature goes down enough, eventually this value is more negative than this is negative, but subtracted so positive. And as a result, the reaction will become spontaneous. Does that make sense? Okay. Now, guys, what about this? Again, we've got negative delta G values are spontaneous. What if enthalpy is positive? What if the change in enthalpy is positive? Does that favor spontaneity? It does not. Guys, what if the change in entropy is spontaneous? Does that favor spontaneity? It does. So if we want this reaction to be spontaneous, now we need to magnify the value for the entropy change because that is tending towards spontaneity. So what do we do to this reaction to make it go? Heat it up. And eventually we can get it hot enough that the value of this offsets the value of that, and now the reaction becomes spontaneous. Does that make sense? Okay, now guys, do this. Make sense of this table. Does it make sense? So guys, this is a summary of everything that we just talked about. So let's look. Join me. Negative delta H, does that favor spontaneity? Yeah. Positive delta S, does that favor spontaneity? Yeah. So the delta G values will always be negative, and this will be spontaneous at all temperatures. Now let's look at the other end of the spectrum. Positive delta H does not favor spontaneity. Negative delta S does not favor spontaneity. Therefore, delta G will always be positive. As a result, it's always non-spontaneous in the forward direction regardless of temperature, but it's spontaneous in the opposite direction. Now, guys, at this point, we need to talk about the tiebreakers. Negative delta H favors spontaneity. Negative delta S does not favor spontaneity. So this factor does not favor spontaneity. So how do we make the reaction spontaneous? We make that smaller by cooling it down. So this will be spontaneous at low temperature, becoming non-spontaneous at higher temperatures. Is that okay? Can you imagine trying to figure this out on your own? You're welcome. Okay, then guys over here, positive delta H, that does not favor spontaneity. Positive delta S does favor spontaneity. As a result, this is now working towards spontaneity, and we want to magnify that. That means that this is, well, we'll start down here. This is spontaneous at high temperature. It is not spontaneous in the forward direction at low temperature. What questions do you have? Yeah. Yeah, it is. But what they're trying to do is they're trying to show you, for example, if this is positive and if temperature is always positive, then the value of this becomes negative. They're just showing you the whole entropy term. But you're right, that is redundant. What else, you guys? We okay? Okay, if you understand the logic, then guys, we've got one more question to answer. What's the elephant in the room? Let's do this. Look here and find the elephant in the room. There's one more important question. Go ahead, Isaac. That's the question. Guys, we've got this idea that it's spontaneous at low and it becomes spontaneous, it becomes not at high, or it's not at low and it becomes spontaneous at high. What does high mean and what does low mean? That's the question that we need to answer. And Isaac, you actually ask it better than I just stated it. Guys, the question that we now need to answer is, what's the tripping point? At what temperature do these reactions change from spontaneous to non-spontaneous and vice versa? So guys, in order to answer that question, I don't have, let me see if there's an example in the book, and if not, we'll just make one up. I'm always reluctant to make these up because I end up with answers that are absolutely wacky. I don't know that I like that though. What is the value for delta G? Yeah, that's no fun. All right, we're just going to make one up. Okay, we'll just make one up. So guys, solve this with me. So let's clean this up. Let's go over here and let's do this. So we've got this equation. You're going to want to have an example. So guys, before we solve this, we need to talk about the logic. But in order to talk about the logic, we've got to make sure you understand what's going on. So let's do this, and I'm just making up numbers. All right, let's do this. I don't like the way I wrote that. So delta G is equal to delta H minus T delta S. And let's do this. The delta H for this reaction is negative. Let's just use easy numbers, and let's not get caught up in significant digits. So guys, let's say the delta H for some reaction, doesn't matter what it is, we'll say that the delta H for the reaction is negative 10 kilojoules per mole. Then let's say that the delta S is 300 joules per mole Kelvin. And actually no, negative 300 joules per mole Kelvin. There we go. All right, so guys, let's talk. Delta H, negative 10 kilojoules per mole. Does that favor spontaneity? Delta H, negative 10 kilojoules per mole. Does that favor spontaneity? Yeah, it's exothermic. Delta S, negative 300 joules per mole Kelvin. Does that favor spontaneity? It does not. So now, guys, will this be spontaneous at high or low temperature? Will this be spontaneous at high temperature or low temperature? Because I'm concerned that you don't know how to think through it. Let me talk you through how to think about this. Here's what you do. The temperature term is contained in the entropy term. So in order to answer the question, you just need to focus there. So negative entropy change, does that favor spontaneity? It does not. Delta S is negative, entropy is going down, that doesn't favor spontaneity. So if this doesn't favor spontaneity, we need to decrease the impact of it on the process. So we need this value to get smaller. So that means the temperatures will be low where this is spontaneous. Yes? So guys, what I would encourage you to do then is somewhere on the paper, even make note to yourself that these are going to be spontaneous at low temperatures. Do you need to talk about that? Then the question becomes this: lower than what? Lower than what? Go ahead. That's it. And it ties back to what Isaac said. What we're going to do, guys, is we are going to make delta G 0. What magic thing happens when delta G is 0? It's at equilibrium, right? So when we say low, we mean lower than the temperature at which it's at equilibrium. So that's exactly what we do. We set delta G equal to 0. Then we plug in our numbers and we solve for T. So delta H is negative 10 kilojoules per mole. Minus T becomes our X, And then, guys, you best be careful. If you just wrote down negative 300, you're sunk. Why? Yeah, guys, your units have got to line up. You can't subtract kilojoules and joules. Let me make a suggestion. It doesn't matter which way you go, but if you convert this to joules, you're going to get 10,000, which to me is a cumbersome number. So what I like to do is always convert joules to kilojoules, because then the numbers are cleaner. So this is negative 0.300 kilojoules per mole Kelvin. Just divide by 1,000, which functionally means move the decimal place 3 spots to the left. Okay, so now we do the math. And we bring this value over, and we end up with 10. I'm going to get sloppy with units. But we bring the value over, and this is 10. And then that gives us 0.300x. Negative x times negative 0.3 is 0.3x. And then, guys, solving for x, we get 10 divided by 0.3, which is 33.3 Kelvin. Yeah, but we're getting sloppy. We're okay. We got a number. So, guys, let's talk about some things about this number. On the AP test, they will not hold you accountable for this. In college, you're going to have university professors that will. This is not a thing. There is no such thing as degrees Kelvin. Guys, the reason is because Kelvin is absolute. When we talk about degrees, that means distances between things. Celsius degrees is the difference between freezing and boiling. Kelvin degrees is the difference between the temperature of salt water and body temperature. Did you guys know that? That's actually how they defined the Fahrenheit scale. The 0 in Fahrenheit was the coldest temperature they could make with salt water. And then they called 100 body temperature. We know now it's 98.6, but they were close. But both Celsius and Fahrenheit we've got fixed points. Then the degrees are steps between. Guys, in Kelvin, this is not steps between. It's 0 Kelvin is 0, and everything goes up from there. So technically, there's no such thing as degrees Kelvin. It's just Kelvin. On the AP test, they won't mark it wrong, but in college, many of your professors will. But guys, understand this is not the answer. And it's not because of significant digits. So guys, let's talk. Remember the initial question. The question was, at what temperature is this reaction spontaneous? And the answer is not 33.3. What's the answer? Yeah. So guys, this is where we bring some ideas together. What happens to this reaction at 33.3 Kelvin? It's at equilibrium. So we know that our answer does not include that value because that's equilibrium. But will the spontaneous temperatures be above or below this? That's why we wrote that down. Do you remember how we got that? We said the idea that delta S does not favor spontaneity, therefore this value needs to be smaller, therefore it will be at temperatures below this. So the way that we then write that is that the temperature of spontaneity will be any temperature below 33.3 Kelvin. Not inclusive. It's not less than and equal to, it's less than. Remember that the alligator eats the bigger number. So the temperature of spontaneity is below 33.3 Kelvin. And you can write that as that. You don't need to write a sentence, but that's it. You guys good? Interesting stuff, right? It's a lot going on, and I understand that. Guys, we are done. Let me present to you your homework. Clean this up. Go back here. Guys, this then is your homework, and the test is on Friday. So guys, we'll take a break when the bell rings. We'll come back. We are going to jump right into lab. and then we'll go from there. I can't wait for you guys to start emailing me when you get to college and you go, oh my goodness, this is saving my butt. Imagine learning all of that stuff in a classroom with 500 students from a professor that barely speaks English. You're going to love it.